Welcome everyone to this presentation. Today we'll explore the power of the method of images in solving complex electrostatic problems and witness the transformative impact of computational techniques in unlocking interesting frontiers in this field. At the heart of our journey lies the method of images, a powerful concept that has played a pivotal role in solving complex electrostatic problems. This elegant approach utilizes the idea of mirroring charges to create a virtual charge distribution that satisfies boundary conditions, allowing us to effectively analyze and comprehend the behavior of electric fields. We then harness the powers of computational techniques to propel our understanding of electrostatics. By implementing the finite difference method, we have developed computer programs that have efficiently and accurately simulated electrostatic conditions.
Method of images. The method of images is a technique used in electrostatic to find electric potential and electric field in a system of charges and conductors. To find this, identify the conductors in a system and determine the desired potential or field in a region. Second, find image charge by reflecting original charge across the conductors. Magnitude of charge is typically the same as that the original charge but with opposite sign. In the last, calculate potential or electrical field created by original as well as by the image charges separately and apply the principle of superposition by adding them.
To derive the potential due to a charge placed in front of infinite conducting plates inclined at an angle of 90 degrees can be done using the method of images. We treat these plates as mirrors, so three image charges will be formed, and the image charges formed due to these negative charges will overlap each other, and these charges will be placed in such a manner that they meet the Dirichlet boundary conditions. And now we can take these four charges as a new system to find the potential at P. Since potential is a scalar quantity, net potential at any point in space will be the sum of potential due to individual charges. The potential due to charge at B at point P can be easily determined if we know the distance PV, and the distance PV can be obtained using the law of cosines, and the potential due to other charges at the point P can be derived in a similar manner. Here is the expression of potential due to all the four charges at the point P.
So now we come to the part where we will be solving this problem using computational techniques. To solve this problem computationally, we will be solving the Ponchon's equation. The Ponchon's equation takes the following form: that square b is equal to some function of x and y. To discretize the continuous form of this equation, we will be using the finite difference method to get an equation like this. Here, the indices I and j represent the point xi and yj. Considering the differences delta x and delta y to be very small, we can equate them to h, which is a quantity which is very small. We can rearrange this equation to get an equation like this. This equation tells us that the potential at each point, Vxi, yj, is actually sort of an average of all the potentials around that point. So the idea is, if we represent this equation and solve it for a finite number of iterations, the solution will finally converge to the true solution. To get a setup, we need an image, and in this setup, the black areas represent our plate where there is 0 volt, and all these yellow areas is actually empty space. We represent our charge density like so, where rho x comma y takes the form of rho, which is constant, at a particular point x comma y, and it is 0 everywhere else. We'll use a charge of 100 coulombs, and it will be shown like this. The black areas, as usual, represent the plates which have 0 voltage. The brown areas is just empty space, and the small yellow area is the charge density. It's a particular point where there's a finite amount of charge equals to 100 coulombs. In this color bar, we represented the value of rho by epsilon naught. And as you can see, it can cross 10 to the power of 13. The final setup looks like so. Here the yellow areas are the areas of 0 voltage, and the charge is represented by this tiny dot. We'll compute the potential using a finite differences method. We'll use an iteration of 10,000. That means we'll be solving the equation for 10,000 iterations. And then we'll plot. As can be seen, the potential at a particular point is high, and the potential gradually follows almost a Gaussian curve with a peak at a particular point. And the potential gets cut at a particular area where there is a plates. So the net potential inside the plates is actually equal to 0. The potential can be plotted on a 3D surface, and there is an interactive plot of the potential where you can see that the potential has a peak and at a particular point and gradually falls down. The other side of the plot shows us that the potential gets cut at a particular point, which is represented by this bump. Moving on, we can find the electric field using this potential as well. The electric field E of x comma y is simply the negative gradient of the potential, and we can calculate the magnitude of electric field by just taking the norm of the two vectors, Ex and Ey, which represent the x and y components of the electric field. And then we can plot it. In this plot is actually inverted to the original setup. Nonetheless, it represents the same thing. In this plot, we see that there's no electric field inside the two plates, which is expected because the plates are actually conductors. And this part, which has two tiny greenish arrows, represents the charge, where the electric field is very high. The magnitude of the electric field is very high. And you see the magnitude of the electric field falls to negligible values as we move away from the plates, which is what we saw in our Gaussian plot.